Okay, so this is the module 3 of kernelized SVM, and we are in lecture 21 and section 4. So in this module 3, I will focus on a practical guide of how do you use SVM in practice.
So what you're going to use is something toolbox called LIBSVM. And there's some other software called SVM Lite or SVM Torch. But until now, LibSVM is the dominating toolboxes people use. And based on all my derivation, you can also tell it's kind of difficult to implement SVM because there are so many things behind. It's not a simple algorithm. So for this homework, we're using the toolboxes. So the steps for using SVM in homework is prepare the feature data matrix, select the kernel functions, select the parameter of the seed, which I haven't even told you what's the seed, but it's one of the important parameters. Without knowing, you can actually just directly try to code, but I'm going to talk about on Wednesday. That seed parameter controls how much you think about the misclassification's importance in the final scoring function versus the margin contribution in the final scoring function. So very important is the data format. I think maybe you already know about it. So actually Panda already hide all the details behind. So maybe this is not very critical, but again, so most SVM toolboxes require the data to be formatted in this specific form. This is actually some form called sparse representation. You can actually tell in this column, I don't have the feature 3 because it's 0. I don't need to represent it. So this is a pretty good form when your feature are sparse. A majority of your the features are 0. You don't need to represent all the zeros using, all the rest until the resolution you like. You can just represent this into a sparse form, which is a very good format to save disk, save memory. This is called, another computational concern, right? We want to have efficient, not in terms of only speed, but also in terms of memory and disk cost. All right, so the other thing is, how do you represent categorical features in this SVM? Honestly, you can design kernels, but in our homework, I feel that's actually too much. So we just use some simple strategy to convert categorical features into called basis vector-based representation, which I think you already had. I think work on the encoding, no, not. So in the end, just if you have discrete features have 3 different possibilities, you're going to use a vector with size 3. If it's red, it's 0, 0, 1. Only one of the entries is 1. And so all the other entries are 0. So this is called basis vector-based representation to represent categorical features. The other important feature, extremely important, it's actually not just for SVM, it's also for deep learning or the other. It's the scaling of your feature. So there are different ways to scale your feature. So we actually talk about in the k-nearest neighbor case, right? If one feature's range is so large, like a weight versus height, and the weight is normally if you use the whatever kilogram of, they're always a much larger number compared to the height. Height number is normally within, if you use inch, it's normally like within the 6 and 0. But the weight is normally like 0 to 300, maybe 200. Yeah. So it's very difficult if you do not normalize your features. The weight feature will dominating over the height feature. So especially if your data are small, and it's very tricky in those cases. So that's why you want to either normalize data or scale data. There are different strategies. Normalization normally pushes all the features into 0 mean and variance 1, or the scaling just push the features to be to be bounded from 0 to 1. And this is the classic equation to scale your data. And there are many different ways. Actually, feel free to read how to do centering only, which means pushes the mean to 0 but doesn't care about variance. Or you also do normalization, you push the mean to 0, variance to 1. Or you only use scaling through those kind of linear conversion by scale it into 0, 1. Yeah, but also very, very important is don't touch your test samples. When you're trying to calculate what is the max, what is the mean, you have to have the max mean or the average to do the centering, right? Don't touch your test data. That's a good practice, just to let you know. Because you should not touch the test data, unless that's a semi-supervised setting. And in the SVM, it's very important to remember, you need to use those scale parameters you use in the training to apply those parameters on the test data. You should not learn a new set of scaling parameter on your test data, then apply on the test. That will be totally destroyed your data. Yeah, it's already 15:18, so and missing values, I mean, you just do frequent value submission, or you use the mean value. There are a lot of tricks. There are also out of dictionary tokens. So if it's a categorical variable, there may be it's just not in your dictionary, which I meant your training data has 4, maybe 3 cases, but in your test data, there's one actual symbol in that feature never happened in your training data, which means your training library doesn't even know what is it. And this is also a classic case called out of vocabulary issues. And this is very classic for natural language processing because in there they have a lot of rare words or new words. There's just no way your dictionary cover all the possible words. So in the end, be careful when you're doing the feature processing of your SVM homework. Out of vocabulary, missing values, centering on scaling data, and also categorical feature representation. And then the last important part is model selection. So how do you select C? How do you select kernels? Again, like we always do. So let's first talk about how to pick C. C is related to the non-separable case SVM formulation, and let's compare the 2 cases. Separable case representation, and just 2 classes can be nicely separated into 2, and there's no noise. There's no noise in the middle. But there are points, of course, on the boundary, right? So more correctly, I should draw this blue points here, red points here, because it's the touching the support vectors. The non-separable case, so I'm touching the points, but at the same time, there are noisy samples on the wrong side. And I'm penalizing the wrong side points distance to the correct plane. So now let's see. So why can't I just always assume it's always separable? If you remember, we had this kernel idea. It's the VC dimension, right? We can always project our x into phi x through RBF kernel. In the RBF kernel, it's like infinite number of dimensions. In that type of formulation, you can always, most cases, separate the whatever finite set of training samples, right? However, so in the end, what we want to balance is we need to consider 2. We want to have a large margin, because large margin represent what? Represent generalization bias on the future data. When you have large margin, so in general, it should be performing actually better because it's not modeling noise too much. So then you really need to balance the complexity of the boundary at the same time the margin size. So let's look at this example. So this example only shows you the linear case. So in the linear case, actually, in fact, you can find a margin that without allowing noise at all. So this is the training cases. So this is the train. So the upper is training with a large C. Large C means penalize error a lot. So this is the training case with a small c, which means I'm allowing some errors. So if you look at this, and yes, this completely separate the two cases. However, the margin is relatively small because you penalize loss more. You really leave very little buffer of the size of the margin. You don't allow the margin to be large. So because of this, I mean, in fact, this just of course a little bit speculated, but just trying to give you the concept. For the future data, it's highly likely to going to make errors because of this 3 points. The only difference is actually before from the large C case versus the small case is actually only 1 point. Is to allow these points to be noisily predicted or not. If you allow that points to be wrongly predicted by using a small c, your margin is actually much larger. It has a better generalization, good region or band separated to classes, and hopefully in the testing data, it can generalize better on the testing data. So in the end, the point is the separable is about, do I make classification errors? And I want to have smaller classification errors, but at the same time, I want to have a good wide band, a wide margin, because this actually is a good bias to hopefully to, not bias, it actually guarantee to regularize my model to behave better. You can actually prove it to regularize my model to behave better in the future data. So balance, margin, and number of error I'm making on training data. Okay, questions about this? So this is the train and this is the test. And the only difference is actually is that point. How do you think about that point? But in fact, if you feel, I mean, just roughly use your eyes, the negative or the red points are quite nicely densely related to each other in this region, and the triangle points are nicely related to each other in this region, right? It's just use your eyes to eyeball. And this margin actually fit a lot better if you think about the more like this dense regions of each of the class. And I'm trying to use the margin to model as wide as I can the density low regions separating the two classes. All right, so that's about the ideas behind margin and a lot of the soft SVM. So, so here is more like a summary of large value. Just means classification is bad, but may lead to more expected training error. And a small c result in more training error, but hopefully a better true error. 12 minutes left, so there's something extra, very extra, like from the kernel. We did not finish last time, so I still want to quickly talk about it. Okay, so kernel, we talk about kernel, right? It's the definition of phi x transposition phi z. And why do SVM work? So now you understand the dual formulation And also the properties of the dual formulation is to make the alpha mostly 0. And now you also learned about kernel representation, which is an implicit way to project data points from X space to phi X space, right? So why do SVM work? You know, X to phi X in the RBF case, it goes to infinite size. Now, like, it's very easy to think about the bias and variance trade-off, right? You have such a flexible model. You're using this infinite size of space to represent my point. Why not overfitting? The reason is, even though it's a huge feature space, the number of parameters remain the same. So let's come back to what I just covered. How many parameters in the dual form of SVM? I just covered. I tried to do the comparison. N. So it's fixed with actually ON, right? It's not about feature phi size at all. It's about alpha, the number of alpha here. So no matter how like flexible that feature space really are, I'm having a fixed number of parameters. The other is we only care about support vectors. Only the support vectors control my W, and there are normally a very small group of vectors. And the maximize of the margin, it's a very good generalization, right? Which we try to have some flavor in the ridge regression case. So why do you want to regularize, right? What do regularization mean? If you still remember, the L2 type of regularization is penalize the large weights, right? You're trying to make the weights kind of similar, not too extreme. So it leads to this, you have to prove it, this type of margin definition leads to the reduce of the overfitting. So the combination is control the parameter size, at the same time control the margin is a regularization. It's two different type of control. But it's extremely flexible at the same time. So just let's review kernel matrix. Really just for all the possible pairwise training data, you're going to calculate kxi(xj), and that kxi(xj) is phi xi transposition phi xj. But you don't need to have explicit form. You only need to just know how to calculate this directly. To in the original form, this is the x transposition x for training, and this is the kernel form. And there's also theorem if if you project it to a really large space, it can in generally very nicely separated or mostly separated by allowing just smaller areas in the margin. So this is the test formulation when using the kernel, using the original feature versus using the kernel feature. You can tell, I mean, almost nothing is changed unless, as long as you have this matrix already available. So this is the RBF proofs, and please, if you're interested, please feel free to watch the video from Caltech, and that specific session gave a really good explanation about RBF and also its projected space and also the properties of the kernel and why. So they're pretty nice summarized. And also we summarize the computational cost is OPN quadratic because you need to calculate all the pairwise, so there are totally n samples. To get that kernel matrix, it's n quadratic operation. For each of the kxij, it needs OP, so this is like OP cost. And then you need to do n quadratic such pairwise computation among all the samples, pairwise samples. This sample versus all the other samples. All right, question about this? So again, OPN quadratic. Okay. So a little bit extra is, so like I roughly said, as long as you have a similarity function, you can be thought of as a similarity measure between the input objects. But it's not every possible similarity measure will work. And there's some certain property you have to guarantee for that kernel matrix. It's the positive semi-definite property, which we actually had some explanation in our regression lesson. So feel free to read why this is the case. It's actually very easy to prove it. Yeah, why that needs to be positive semi-definite. Okay, so now next is the most tricky part of using SVM is what kernel function to use. And the kernel function is important because it summarizes almost everything about the data. I don't even use the X at all. I only use K. I only use that matrix, kernel pairwise similarity relationships. So, but this actually is also good, right? Because for a lot of domains, it's very difficult, like I said, to come out the numerical representation of X, but it's very easy to come out a similarity function among the objects, like string to string, graph to graph, string to string, graph to graph, or maybe some sets to sets. So all those discrete type of data structures can design some similarity functions. Then you can use the whole paradigm of support vector machine to perform very nicely theoretically guaranteed classification. So kernel trick is really helped non-traditional data to be able to fit into the formulation to perform nicely formulated classification, theoretically guaranteed. It's a good balance of bias and variance trade-off, right? If you remember, it's fixed size of parameters, regularization through the margin or through the L2 norm. So it's pretty difficult, like if you think about Cambridge neighbor and all those, and it's not that easy to add all those other terms to regularize. However, SVM is a good combination of those framework from STAT and plus this flexibility of designing the kernel functions to make them work on non-traditional data. All right, so you might go confused about this definition called kernel. And if you already learned in some other classes something called kernel regression, the kernel here is different from the kernel, the definition of kernel in those kernel regressions. You can think about the support vector machine's kernel, it's the Mercer kernels, and those kernel regression-based kernels are called smoothing kernels. So this is totally extra. Feel free to check it out. So, but they are actually two different concepts. All right, you can make the choices with RBF or polynomial kernels. There are also a lot of kernels, other type of kernels provided by LIBSVM. But you have to tune the parameter of RBFR or maybe gamma. And you also need to control this parameter. There are two parameters here, the D. So there are C. There are also kernel-specific hyperparameters. How do you select? You do grid search. So you try all the possible values of those hyperparameters. And inside cross-validation on train to pick the best combination of hyperparameters reflected on the cross-validation. But you don't do tests in your current formulation because the test, there's no label in the test. So we are the person who give you the test performance. So you have the test data, but you don't touch the test data in the cross-validation and use those all in to apply your best learned hyperparameters, and then retrain the whole model using the best hyperparameter configurations, got this full model, and apply on the test data we share with our labels, and then submit that predicted label files. And this is more like a simulation of where imitate how truly like a Kaggle competition or those. So you do cross-validation to pick the best hyperparameter, and there's the organizers to judge who's the best. And this is the more details provided from the scikit-learn that Preprocessing, and I think it's a pretty good guide. And in general, RBIF is a very nice, solid kernel. All right, so this is more provided by the scikit-learn Preprocessing guide. Just feel free to check it, follow their pipelines, and this is everything we want to cover about SVM.